May 9, 1941. A cold rain falls across the gray waters of the North Atlantic, 200 miles south of Iceland. Aboard the German submarine U-110, Captain Lieutenant Fritz Julius Lemp stands in the control room, hands gripping the periscope housing as depth charges explode in the black water around his vessel. The hull groans, rivets strain. In the dim emergency lighting, young submariners with pale faces and trembling hands await orders. Above them, British destroyer HMS Bulldog circles like a patient predator. Lemp has spent 3 years perfecting the art of evasion, 3 years trusting absolutely in German naval superiority, 3 years believing that the Kriegsmarine's communications remain impenetrable to enemy intelligence. He believes this even now, as his batteries fail and toxic chlorine gas begins seeping from the damaged electrical systems. He believes it as he gives the order to surface, expecting to scuttle his vessel and escape in lifeboats. He believes it as the submarine breaks through the surface and British sailors, contrary to every expectation, do not immediately open fire but instead launch a boarding party. What Lemp does not know, what he cannot know as he watches from the freezing water, having abandoned ship, is that in the cramped radio room of U-110, bolted to a small desk still warm from the radio operator's hands, sits a gray metal box roughly the size of a typewriter. It is an Enigma machine, and its capture, along with the codebooks and rotor settings stored nearby, will mark the beginning of the end of German confidence in the invincibility of their ciphers. The mockery had begun years earlier, in the quiet confidence of German military superiority. Throughout the 1930s, as the Wehrmacht rebuilt itself in defiance of Versailles, as U-boats slid from hidden shipyards into the Baltic, as Luftwaffe pilots trained in secret, German cryptographers perfected what they believed to be an unbreakable communication system. The Enigma machine, invented in the 1920s for commercial use, had been adopted and modified by the German military into something far more sophisticated. Its genius lay in complexity layered upon complexity, 3 rotors, later 4, each with 26 possible positions, cycling through electrical pathways that transformed each keystroke into a different letter according to a mathematical permutation that changed with every press. A plugboard added further substitution. The number of possible settings exceeded 150 million combinations. To German engineers and military planners, this represented not merely security but absolute certainty. They calculated that even if an enemy captured an Enigma machine intact, without knowing the daily settings, which rotors to use, their starting positions, the plugboard configurations, breaking the cipher would require testing every possible combination, a task that would take longer than the age of the universe using conventional methods. This confidence bred arrogance. In German military academies, instructors taught that Allied cryptanalysts, if they existed at all, were wasting their time pursuing phantoms. Intelligence officers openly discussed sensitive operations over Enigma encrypted radio, believing their words as secure as if spoken in a locked room. Admiral Dönitz, commander of the U-boat fleet, coordinated his wolf pack attacks through detailed radio communications, directing submarines across thousands of miles of ocean, with precise instructions that he believed remained invisible to the enemy. The fundamental assumption was simple. German engineering had created something beyond the reach of Allied mathematics. The Enigma was not simply a cipher machine. It was a symbol of German intellectual and technological superiority, proof that the master race could outthink as well as outfight its enemies. When, in the early years of the war, U-boats sank Allied shipping at catastrophic rates, in 1940 alone, German submarines sent over 4 million tons of Allied shipping to the bottom of the Atlantic. It seemed to confirm what German commanders already believed, that their communications remained secure, their movements unpredictable, their strategies invisible to enemy understanding. But across the English Channel, in a Victorian mansion in Bletchley Park, 50 miles northwest of London, a very different story was unfolding. The estate, requisitioned by the British government in 1938, had been transformed into the Government Code and Cipher School, though this bland name concealed the most ambitious cryptanalytic effort in human history. Here, in a collection of temporary wooden huts erected on the mansion's lawn, mathematicians, linguists, chess champions, crossword enthusiasts, and scholars gathered under conditions of absolute secrecy to attempt what German engineers had declared impossible. They came from Oxford and Cambridge, from civilian life and military service, united by a single purpose: to break Enigma. Among them was Alan Turing, a 27-year-old mathematician whose theoretical work on computation and machine intelligence remained largely unknown outside academic circles. Turing understood something fundamental that German confidence had obscured: that the Enigma's complexity, while vast, was not infinite. Its security rested on the assumption that certain mathematical shortcuts were impossible, that certain patterns could never be detected, that the human operators who used the machine would never make mistakes. Turing believed otherwise. He saw the Enigma not as an impenetrable wall but as a mathematical problem susceptible to systematic attack. The work was brutal in its tedium. Each day, Enigma settings changed at midnight. Each day, the codebreakers began again from nothing, racing against time to decrypt messages before they became obsolete. The process relied on cribs, probable plain text phrases that might appear in encrypted messages. German radio operators, despite instructions to avoid predictability, were human. They began weather reports with standard formulations. They ended messages with predictable sign-offs. They used the same phrases to describe routine operations. These habits, tiny cracks in operational security, gave the codebreakers footholds. Turing designed an electromechanical device he called the bomb, a machine that could test thousands of rotor positions per minute, searching for configurations that would transform the encrypted text into known German phrases. The first bomb became operational in March 1940. It was 6 feet tall, weighed a ton, and contained over 90 rotating drums that clattered with a sound like 1,000 knitting needles working in unison, a sound that became the signature rhythm of Bletchley Park, the mechanical heartbeat of a new kind of warfare. Yet success remained sporadic. Breaking Enigma required not only mathematical brilliance but also physical intelligence, the actual capture of machines and codebooks from German vessels. The Royal Navy understood this. They launched operations specifically designed to capture Enigma materials from weather ships, U-boats, and naval vessels. Each capture was a calculated risk. If the Germans suspected their cipher had been compromised, they would change procedures and all previous work would become worthless. The boarding of U-110 in May 1941 represented a breakthrough of extraordinary magnitude. For the first time, the British captured not only an intact naval Enigma machine, but also the complete codebooks and cipher settings for the month. The intelligence hall, transferred in absolute secrecy to Bletchley Park, allowed the codebreakers to read German naval communications with unprecedented clarity. For weeks afterward, the submarine tracking room in London possessed what amounted to a window into Dönitz's strategy, seeing his orders almost as soon as his U-boat commanders received them. Convoys could be rerouted away from wolf pack concentrations. Anti-submarine forces could be directed toward known U-boat positions. The hunters became the hunted, and they did not understand why. The German response to increasing U-boat losses throughout 1940 was not suspicion of compromised communications, but rather a deepening of their original assumptions. If U-boats were being found and destroyed with greater frequency, German intelligence reasoned, it must be due to improved Allied radar, to better anti-submarine tactics, to aerial reconnaissance, to anything except the possibility that Enigma had been broken. The machine remained, in German understanding, fundamentally unbreakable. This cognitive blind spot, the inability to question a foundational assumption even as evidence mounted against it, represented a failure not of German engineering, but of German imagination. They had created a system so complex that they could not conceive of its defeat. Admiral Dönitz, reviewing casualty reports and operational data, ordered investigations into radio discipline, into the possibility of Allied direction-finding technology, into whether U-boat commanders were maintaining proper silence during operations. He never ordered an investigation into whether the enemy was reading his mail. The Enigma machine became a symbol not of security, but of misplaced faith, of the danger that comes when technological confidence replaces skeptical vigilance. Through 1942 and 1943, as American industrial capacity joined the Battle of the Atlantic, the intelligence advantage from broken Enigma codes became increasingly decisive. The codebreakers at Bletchley Park, expanded now to over 9,000 personnel working in shifts around the clock, were reading not only U-boat communications, but also Luftwaffe signals, Wehrmacht traffic, SS administrative messages. The wooden huts hummed with the sound of bombs. By war's end, over 200 of them would be operational, testing rotor settings in a never-ending mechanical search for daily keys. The intelligence product, codenamed Ultra, flowed to Allied commanders through carefully controlled channels designed to protect its source. Churchill received daily summaries. Eisenhower planned operations with knowledge of German dispositions. Montgomery knew Rommel's supply situation in North Africa. Naval commanders routed convoys with awareness of U-boat patrol zones. The advantage was asymmetric and devastating, yet it remained invisible to the enemy. German commanders, reading reports of their own losses, attributed them to Allied material superiority, to numerical advantage, to better tactics and training, but never to the fundamental compromise of their communication security. The symbolic object that represented this transformation was not a weapon or even the Enigma machine itself, but rather the simple metal rotor, the 3 or 4 wheels that determined Enigma's electrical pathways. Each rotor was a disc about 4 inches in diameter, made of bakelite or rubber, with 26 spring-loaded pins on one face and 26 corresponding electrical contacts on the other. The internal wiring of each rotor created a unique substitution cipher. As the rotors turned with each keystroke, the cipher alphabet changed continuously. To German engineers, these rotors represented the perfection of cryptographic security, the embodiment of mathematical certainty. To the codebreakers at Bletchley Park, they represented a puzzle to be solved through systematic analysis, through the exploitation of human error, through the application of logic and machinery to a problem of staggering but finite complexity. The rotor became a symbol of the war's deeper truth, that no technological advantage remains permanent, that every system contains vulnerabilities, that confidence in invulnerability is itself a vulnerability. In British hands, rotors captured from U-110 and other sources became teaching tools, objects of intense study, keys to understanding the enemy's keyspace. In German hands, they remained objects of faith, their security assumed rather than verified. By February 1943, the Battle of the Atlantic reached its crisis point. In that single month, U-boats sank 63 Allied merchant ships totaling over 350,000 tons. Dönitz believed he was winning the war of attrition, bleeding the Allied merchant fleet faster than shipyards could replace losses. He coordinated his wolf packs through detailed Enigma encrypted messages, positioning submarines across convoy routes with precision that would have been impossible without radio communication. He remained supremely confident in his operational security, but March 1943 brought a sudden, inexplicable reversal. Allied convoys began evading U-boat patrol lines with uncanny precision. Anti-submarine aircraft appeared over U-boats that had maintained radio silence. Destroyer groups arrived at patrol zones exactly when submarines were concentrated there. In May 1943, Dönitz lost 41 U-boats, nearly one-quarter of his operational force, in a single month. The losses were unsustainable. On May 24, 1943, he withdrew his U-boats from the North Atlantic, effectively conceding defeat in the battle that had raged for nearly 4 years. The withdrawal marked a strategic turning point. Without control of the Atlantic, Germany could not prevent the buildup of Allied forces in Britain, could not interdict the flow of American supplies, could not isolate the British Isles. The invasion of Fortress Europe became inevitable. Still, incredibly, German confidence in Enigma persisted. The Kriegsmarine conducted investigations into the May losses. They examined whether U-boat commanders had maintained proper radio discipline, whether the Allies had developed new radar frequencies that German detectors could not sense, whether Allied anti-submarine aircraft had acquired new weapons or tactics. Internal reports considered every explanation except the one that was true, that the enemy was reading their communications in near real time, that every encoded order from Dönitz to his submarines was being intercepted, decrypted, and analyzed within hours by the codebreakers at Bletchley Park. In July 1943, German naval intelligence produced a report concluding that compromise of Enigma remained practically impossible, given the machine's complexity and the mathematical improbability of breaking its cipher. The report noted that even with captured machines and documents, without daily settings, the Allies would require resources far beyond their theoretical capabilities. This conclusion represented a catastrophic failure of intelligence assessment, but it was a failure rooted in the original sin of overconfidence. Having decided that Enigma was unbreakable, German analysts interpreted all subsequent evidence through that lens, discarding explanations that challenged their fundamental assumption. The transformation in Allied fortunes touched every theater of the war. In the Mediterranean, British forces in North Africa used decrypted Enigma traffic to identify Rommel's supply convoys, then directed submarines and aircraft to destroy them. The Afrika Korps fought brilliantly, but could not overcome the fundamental disadvantage of operating at the end of supply lines that Allied intelligence could target with precision. In the Atlantic, the flow of merchant shipping that sustained Britain's war effort continued uninterrupted after May 1943, allowing the buildup of millions of tons of equipment and supplies for the eventual invasion of Europe. In the air war over Germany, RAF Bomber Command used decrypted Luftwaffe communications to identify fighter concentrations and adjust bombing routes accordingly. The intelligence advantage was not absolute. Ultra did not prevent defeat, did not eliminate casualties, did not make victory certain, but it tilted every engagement, reduced every risk, increased the probability of success in ways that compounded over thousands of operations across years of war. Historians would later estimate that access to Enigma decrypted intelligence shortened the war in Europe by 2 to 4 years, saved hundreds of thousands of lives, and prevented the starvation of Britain during the darkest months of the U-boat campaign. The exposure of Enigma's vulnerability came not through German discovery, but through gradual Allied success that the Germans could no longer ignore or explain away. By 1944, as Allied forces advanced across Europe after D-Day, captured German documents and interrogated prisoners revealed a dawning awareness that something had gone terribly wrong with communication security. Some German officers began to suspect that their codes had been compromised, though they could not understand how or to what extent. The full truth remained hidden even then, protected by Allied security measures that would keep ultra secret for 3 decades after war's end. But the pattern of German defeats, the consistent failure of supposedly secret operations, the inexplicable Allied ability to appear at decisive points with superior force, These realities forced a slow, painful revision of German assumptions. The Enigma machine, once a symbol of technological superiority and cryptographic invincibility, became a symbol of failure, of the hubris that comes from confusing complexity with security, of the fatal mistake of believing one's own propaganda about intellectual supremacy. For the young German submariners who had gone to war believing in the invulnerability of their communications, the revelation came through accumulated loss that transcended rational explanation. Men who had survived years of Atlantic patrols, who had executed tactics perfected through hard experience, who had trusted absolutely in the security of their radio orders, found themselves hunted with a precision that seemed supernatural. Of the 39,000 men who served in German U-boats during the war, 28,000 died, a casualty rate of 72%, the highest of any service branch in any nation's military. Many of these deaths came after mid-1943, after Bletchley Park had achieved consistent success in breaking naval Enigma, after the Allies had transformed signals intelligence into a weapon of systematic destruction. The U-boat crews did not die because they lacked courage or skill. They died because they were visible to an enemy they believed was blind, because they trusted a system that had been compromised, because their leaders' confidence in German technological superiority prevented them from questioning whether the impossible had become real. They went into battle carrying faith in the Enigma machine like a talisman, never knowing that this faith betrayed them. The change in perception, when it finally came, was devastating in its implications. German military officials who had mocked the idea that Allied cryptanalysts could break Enigma, who had dismissed concerns about communication security as defeatist pessimism, who had staked their operational planning on the absolute reliability of their cipher systems, faced the slow realization that they had been fundamentally wrong. The mockery turned inward. Post-war analyses revealed the extent of the disaster. Nearly every major German military communication had been compromised, read, analyzed, and disseminated to Allied commanders. Operations planned in secret had been known to the enemy almost immediately. Tactical movements coordinated through supposedly secure channels had been anticipated and countered. Strategic deceptions had failed because the true intentions were visible in decrypted traffic. The psychological impact on German military officers who learned this truth after the war was profound. They had lost not because they were outfought, but because they were outthought, not because their warriors were inferior, but because their assumptions were wrong, not because their technology failed, but because their understanding of its limitations was incomplete. The rotor, that small mechanical component at the heart of the Enigma system, became in retrospect a symbol of the war's deepest lessons. In German hands, it represented the belief that engineering excellence and mathematical complexity could guarantee security, that technological advantage once achieved would persist, that the ingenuity of the master race exceeded the capabilities of their enemies. This belief was not merely propaganda, but a genuine conviction held by intelligent, educated, technically sophisticated officers and engineers who should have known better. Their failure was a failure of imagination, an inability to conceive that others might match their intelligence and exceed their dedication, that the apparently impossible might be achieved through methods they had not anticipated. In Allied hands, the captured rotors represented something different. The triumph of collaborative effort over individual genius, of systematic method over intuitive brilliance, of persistence over confidence. The codebreakers at Bletchley Park succeeded not because they were smarter than German engineers, but because they were more skeptical, more willing to question assumptions, more open to unconventional approaches, and more humble about the limits of their own certainty. Alan Turing, whose theoretical work and practical machines made the breaking of Enigma possible, would later reflect on the nature of the achievement with characteristic modesty. He understood that the success came not from a single breakthrough, but from the accumulation of small advantages. The capture of machines and codebooks, the identification of operator errors, the exploitation of predictable message formats, the development of increasingly sophisticated bombs, the recruitment of thousands of skilled analysts, and the systematic organization of intelligence product. No single element would have sufficed. The victory over Enigma required an industrial-scale effort applied to an intellectual challenge, the marshalling of resources and talent on a scale that Germany, despite its technical sophistication, had not imagined necessary for cryptanalytic work. Turing recognized that the Germans had been defeated not by a failure of engineering, but by a failure of institutional imagination. They had created a machine they believed unbreakable, and therefore had not prepared for the possibility of its compromise. This lack of contingency planning, this inability to question foundational assumptions, proved more fatal than any technical flaw in the Enigma itself. The liberation of occupied Europe in 1944 and 1945 brought Allied soldiers into contact with German military personnel who remained, in many cases, unaware of the extent to which their communications had been compromised. American and British interrogators, bound by secrecy agreements that would last for decades, could not reveal the true source of Allied intelligence advantages. German officers, surrendering after years of fighting, offered explanations for their defeat that focused on material superiority, on the weight of Allied numbers, on the opening of multiple fronts, on the devastating effect of strategic bombing. These factors were real and significant, but behind them, invisible to German understanding, lay the quiet triumph of the codebreakers, the patient work of mathematicians and linguists who had turned the Enigma machine from a symbol of German confidence into a source of German defeat. The supreme irony was that the weapon that most effectively turned the tide of war was not a new tank or aircraft or bomb, but rather information itself, the knowledge of enemy intentions, dispositions, and plans that came from reading supposedly secure communications. The full truth about Enigma's compromise remained classified until 1974, nearly 3 decades after the war's end. When the story finally emerged, it fundamentally revised historical understanding of the war's course. Victories that had been attributed to Allied military superiority or German tactical errors were revealed to have been influenced, sometimes decisively, by intelligence advantages stemming from broken ciphers. The skill of Allied commanders, while real, had been amplified by information they should not have possessed. The courage of individual soldiers, while genuine, had been supported by operational planning that benefited from enemy communications read in real time. The German military, which had been defeated in detail across multiple theaters, could finally understand one of the central reasons for their defeat. They had been fighting blind against an enemy who could see. The revelation was humbling for historians who had crafted narratives of the war without knowing this crucial dimension, and it was devastating for surviving German veterans who learned that their sacrifices had been made, while their most fundamental assumptions about communication security were catastrophically wrong. For Fritz Julius Lemp, the U-boat commander whose vessel U-110 was captured in May 1941, there would be no learning of this truth. He died in the cold waters of the North Atlantic, watching British sailors board his abandoned submarine, believing to his last moments that he was preserving security by destroying his vessel's secrets through scuttling charges that he expected to detonate. The charges never fired. The submarine remained intact. The Enigma machine, along with its codebooks and rotor settings, fell into British hands and was rushed to Bletchley Park, where it accelerated the breaking of naval Enigma and contributed to the deaths of thousands of his fellow submariners in the years that followed. Lemp's final act, intended to protect German security, instead became instrumental in German defeat. His story encapsulates the tragedy of misplaced confidence. Brave men executing their duties skillfully, while operating under assumptions that had been invalidated by events, they could not perceive, and realities they had been taught to dismiss as impossible. The story of Enigma and its breaking is ultimately a story about the danger of certainty, about the catastrophic consequences that follow when technological confidence replaces critical thinking. The German military entered the war with a cipher system they believed to be unbreakable, and this belief shaped their operational security, their communications procedures, their planning assumptions, and their responses to mounting evidence of compromise. They created a machine of extraordinary sophistication, then treated it as magic rather than mathematics, as absolute protection rather than significant obstacle. This category error, mistaking difficult for impossible, complex for invulnerable, exemplifies a deeper truth about human cognition and organizational behavior. We are most vulnerable precisely when we are most confident, most likely to fail when we are most certain of success, most easily defeated when we believe defeat to be impossible. The German military, trained to value precision and discipline, fell victim to intellectual rigidity, unable to question axioms even as those axioms led inexorably to disaster. The Allied victory over Enigma demonstrated a contrasting truth: that humility in the face of complexity, that skeptical questioning of assumptions, that willingness to attempt the apparently impossible, can yield results that transform history. The codebreakers at Bletchley Park did not know at the outset that they would succeed. Many of them doubted whether Enigma could be broken at all, but they proceeded anyway, applying systematic methods to an overwhelming problem, building machines to attack machines, recruiting unconventional talents to solve unconventional puzzles, and maintaining their efforts through years of partial success and frustrating setbacks. Their persistence was not rooted in confidence but in necessity, not in certainty of victory but in commitment to the attempt. This distinction matters. The Germans failed because they were certain they could not fail. The Allies succeeded because they refused to accept that failure was inevitable. The mechanical clatter of the bombs at Bletchley Park, that sound of rotating drums searching through millions of possible Enigma settings, became the signature rhythm of a new form of warfare. A war fought not with fire and steel alone, but with mathematics and machines, with logic and perseverance, with the systematic application of human intelligence to challenges of mechanical complexity. This sound, this industrial heartbeat of code breaking, represented the transformation of intellectual work into strategic advantage, the weaponization of thought itself. It was the sound of modernity asserting itself in war, the sound of a future in which information would become as valuable as ammunition, in which knowing the enemy's plans would matter as much as destroying his forces, in which wars could be won by mathematicians working in secret before generals fought in the open. The Germans who mocked Allied code-breaking capabilities, who believed that the complexity of Enigma placed it beyond reach of enemy cryptanalysis, who assumed that German engineering had created an invulnerable system, never heard this sound, never understood what it represented, never grasped that their certainty itself had become their greatest vulnerability. In the end, the breaking of Enigma teaches a lesson that transcends the specific history of World War II. It teaches that confidence, however well-founded, must be tempered with skepticism. It teaches that technological advantage is never permanent, that any system created by human minds can be understood by human minds, that complexity delays but does not prevent defeat. It teaches that organizational culture matters as much as technical capability, that the willingness to question axioms and challenge assumptions can be more valuable than engineering excellence. Most fundamentally, it teaches that mockery of one's enemies, contempt for their capabilities, certainty about one's own superiority, these attitudes do not merely fail to protect, they actively harm by blinding institutions to emerging threats and preventing the adaptation necessary for survival. The Germans who mocked Allied codebreakers learned, too late and at terrible cost, that the last laugh belongs to those who remain humble enough to question, skeptical enough to verify, and flexible enough to adapt when their certainties prove false. The rotor turns, the cipher changes, but the lesson remains. In war as in peace, the greatest danger comes not from enemy strength but from our own unexamined assumptions about weakness, not from their capabilities but from our certainty about their limitations, not from what we do not know but from what we are certain we know that proves to be